All right. So last week we went through all the problems on practice exam A. All the practice exam B problems should be up. Should be able to see it on YouTube, kind of what I did in my other section. But if you have questions over those, we can go over some of those today. I'll kind of first take any questions, specific questions anyone has. If we run out or don't have any, I guess I'll just kind of pick probably some of the hypothesis testing ones that come from practice exam B probably to work through. But before I do that, I'll kind of leave open. Is there anyone that has a specific problem or even just a general question kind of that you want to go over before the exam?
Like the email sent number 12 is one.
Mm-hmm.
You just kind of
Yeah, so I'll get that updated today at some point where I'll kind of give everybody full credit. It didn't instantly happen as soon as it was due, so I still need to go through and make sure I give everybody credit for number 12 on that Connect homework. Any other questions, specific problems, or just general questions about a specific topic? Yeah.
Honestly, on exam A on number 16.
Okay. Let's see. Exam A, 16. So let's see, what was that one? Okay, so just a little bit, I'll probably, whatever question I get, I'll probably speak to that question and just kind of in more general types of questions like this. So here we've got some information that we were given about, we found a sample salary for dentists and we had a sample size of 30. We've got a sample standard deviation. So right away, I mean, 16, this doesn't necessarily apply, but what distribution should we be thinking about? Anytime we see this word sample variance or sample standard deviation, automatically we're using what distribution? Remember from last class. So this is one way I would keep track of how you always figure out which type of distribution to use. So anytime you see this word proportion, right? Or kind of think about we're dealing with these sample proportions, right away, you know that you're using a standard normal distribution. So if you see that word proportion, now we didn't have that in this problem, but a different problem we could have seen that. The other two types of examples are we have sample means, but one of them, kind of you'll know the population standard deviation or you'll know the population variance. So you'll have either the population standard deviation or you'll have the population variance. Anytime you know that population standard deviation, you're still using that standard normal Z table. Anytime you see that you have a sample standard deviation or a sample variance, right? Or you're given S or S squared, those are the only times we use that student T distribution, at least for the examples that we have so far, okay? So we had a sample standard deviation that was given to us. So any of these problems that we look at, using this information, we should be using that student T distribution. Now we have a sample mean, but what we want to know with hypothesis testing your confidence intervals is where is that true population mean, right? Or what is possible values that we could reject for that true population mean, which is what 16 is getting at, right? So suppose that this news article says the average salary is 150,000, and we want to test just for whether or not the true average salary is less than that amount. Right? So whatever you want to test for, right, or whatever you're trying to find, which in this case is whether or not the true average salary is less than 150,000, that's our alternative hypothesis. So right away we could write out that what we're trying to find is that true mean kind of less than, I'll write this over here, what, 150,000, right? That was the reported amount. So we'll assume the exact opposite is true, which that will be our null, what we're assuming to be true, which is that mean, what's the exact opposite or what's the complement? Well, here, what we wanted to find was that it was less than 150,000. We'll assume that's greater than or equal to 150,000. Okay? So whatever the problem kind of gives you, whatever you're trying to test for, right, that's going to be your alternative hypothesis. So here we want to find is it less than 150,000. Now, if we wanted to say find is it different than 150,000, well, that would have been is that mean different than or not equal to 150,000, which would make our kind of null. We would assume it's equal to. Now, this wasn't the case. I'm just giving you kind of other examples there. But yeah, whatever the kind of problem states is what you're trying to test for, kind of write that down as your alternative hypothesis, and then assume the exact opposite or that the complement is true. Okay? Yeah.
So for like 17, 18, I would be using the t-table all the way down.
Yep, so once we know that all we have is a sample standard deviation, we are looking for what that true population mean is, but when we do the hypothesis test, we have to find critical values and test statistics. For example, 18. When we say this is a test statistic, right, we kind of have multiple types of test statistics for these different types of problems. You can almost think about it this way, right? So for the proportion or a sample mean where we know the population standard deviation, we're dealing with that standard normal distribution, so our test statistics will be z-statistics. We only have a sample standard deviation with a sample mean. Here we can kind of think about we're using the student t-distribution, so our test statistic is a t-statistic because it comes from a student t-distribution, yep. So like that test statistic will kind of be coming from a student t-distribution. If we want to find these critical values, which are kind of the cutoffs for which if we see any test statistic more extreme than the critical value, then we can reject. So what we'd be thinking about there, I'm going to draw this out here. Like on 17, we know we're using that student t-distribution, and I think we'll be using the one where the degrees of freedom is what? N minus 1. I think our N was 30. So degrees of freedom 29. So if we have a what type of tail test, we have a less than sign in the alternative hypothesis. So we have kind of this left tail test. So we know we're looking at the left side or less than left tail of the distribution. So like if we just wanted to find one critical value, it'd be a critical value that gives us kind of alpha in this lower left tail. Well, this critical value is just a cutoff value, right? It's coming from the student t-distribution, so it really is a t-value, right? We'll get it from that student t-distribution. We would then do is once we had that test statistic, well, where does our kind of test statistic or our t-statistic in this case fall? If it's not more extreme than the critical value, right? It's not in that rejection region, we would fail to reject. If it ends up being somewhere over in that rejection region, well, it's in the rejection region, and that's the case where we reject. So we could find those critical values, right? And we'll just kind of think about the alphas that we would have here of 0.1, 0.05, and 0.01. We go to that student t-table at degrees of freedom, oops, 29, so it's going to be pretty far down. So 0.1, 0.05, and 0.01 were the three alphas we wanted. So we go down, oops, degrees of freedom 29, 1.311, 1.699, 2.462. Now, the one thing we have to remember are those are the values we want, but remember the student t-table is looking at the right side of that distribution. So if this was a right-tailed test, we're done, right? But we had a left-tailed test, so it's going to be those three critical values, right, for those three different alpha levels, but negative. So negative 1.311, negative 1.6 something, I forget already. So if we go kind of here, right, it'd be these guys right here, right? Those values, but negative. And we should have known that it had to be A or C here, because once you figure out you've got this left-tailed, this less than kind of test, your critical values have to be negative. You can then find the test statistic, but here I'll always kind of then, if I ask you about a rejection decision, I'll give you an assumed true test statistic. That way, like if you calculate it incorrectly, you don't have cascading errors. So calculating the test statistic is really just a matter of identifying the correct equation, right? So when we go to that formula sheet, here are three test statistics, our different types of examples. We have one where we have a sample mean, but we only have a sample variance or a sample standard deviation. So at this point, it's just a matter of plugging in the values that you're given. We had 145,000 as a sample mean. What? The sample standard deviation was 10,000. So that's just S. So we plugged 10,000 in for S, so we'll still have to square it. And then our sample size here was 30. The only other thing we need is that assumed true mean, right? Which comes right from your null and alternative hypothesis, which for us, right, would have been 150,000. Right? So the test statistic is just a matter of kind of identifying the correct formula and then kind of getting it plugged into your calculator correctly. Right? You'll be giving all the information, so it's just a matter of kind of getting that plugged into your calculator. Now, when I give you that assumed true test statistic, right? If we were thinking about making rejection decisions, I told you to assume it was negative 1.5, right? So everybody's starting from kind of the same place, right? No cascading errors here. Well, we already have the critical values. Right? So if I plotted my critical values up here, we had what? Negative 1.311, that was the 10% level. Negative 1.699, that was the 5% level. And I forget, this was negative 2.4 something. 462. All right, so that was the 1% level. Our rejection regions are anything more extreme or larger in absolute value, or kind of draw the arrow into the tail. That's another easy way to remember it. So where does our test statistic fall? It was negative 1.5, so that would be here. Right, that was my T statistic. Well, that's in the rejection region at the 10% level, so I rejected the 10% level. It's not quite in the rejection region at the 5% level, so I failed to reject there. And if it's not in the rejection region at the 5, it's definitely not going to be in that rejection region for the 1. So the only level I can reject that would be that 10% level. That's how I would go about and kind of make those rejection decisions. Now that's using the critical value approach. What other approach could I have used? Kind of that p-value. All right, so what would that have looked like? Well, there, I could almost like, I'm going to leave it up here in case people are writing, but I could get rid of all this critical value stuff. And the p-value is just the probability that I saw something that gave me the test statistics that was that far away from the assumed true mean, or any further. So kind of this entire red area would be my p-value. Now for a one-tailed test, this is easy. I don't have to think about anything on the other side, right? So I just want the area to the left of negative 1.5. Well, it's a little bit trickier with a student t-distribution, because when I go to the table and try to find the area to the left of that, I run into two kind of issues, right? One, this is the right side of the distribution. Well, it doesn't really prevent me from doing it. I just can think about the left side would be all these same values, but negative, right? So I go down here to my degrees of freedom. Where would kind of negative 1.5 fall if all these values were negative? Somewhere in between these two, right? Well, if I know the area to the left of negative 1.3 is 0.1, and the area to the left of negative 1.7 is about 0.05, then the area to the left of negative 1.5 is somewhere in between that range. So somewhere in between 0.05 and 0.1. So all I can really say there is my p-value is somewhere in the range of 0.05 to 0.1. Well, that's okay, because if I'm making my rejection decision now using the p-value, I only reject if the p-value is less than alpha. So if my alpha was 0.1, well, my p-value has to be less than that, right? That's kind of what my bounds told me. So I would reject at that level. Is it less than 0.05? Well, in fact, the bound tells me no, it has to be greater than 0.05, so I would fail to reject. And if it's greater than 0.05 here, it's definitely not going to be less than 0.01. It has to be greater than, so we would end up making the same rejection decisions that we did before. Now, I would say with the student t-distribution examples, it's probably easiest to use the critical value approach. I think when we have a standard normal distribution, because you can get one specific value for that p-value, you don't have to kind of put bounds on it. It's probably easier to use that p-value approach. Now, in a lot of these problems, I'm like asking you both, it's not like you have the freedom, but if you had like a short answer example or something where I asked you to kind of do this, taking the p-value approach is a little harder with the student t-distribution. Unless I were to give you like a test statistic that happened to be one of those exact values that were on the table. Okay? Any other? Yeah.
Can you do 14 through 19 on these?
14 to 19. Yeah, we can work through some of those.
There's those 5 for, I think, public testing.
Yeah, let me see. So this is A. Make sure I don't have any. Okay. All right, so we'll go down to 14. Okay, so this will be a good one to go through. So for the very first one, we're just told, let's assume I have this sample of 49 Ball State students. They have a sample mean of 109, and I have a known population standard deviation of 15. So if I know the population standard deviation, what distribution should I be thinking about for the next, what, 5 questions? This isn't a proportion, right? But it's a sample mean where I know the population standard deviation. Yeah, so if I don't see that I only have a sample standard deviation, that means student T. Well, I don't have a sample standard deviation here, I have a population standard deviation, so I'm using that Z table, right, or that standard normal distribution. So that's kind of what this one is asking. Should you use the student T or the standard normal? Well, no, we're using the standard normal here because we know the population standard deviation, which is what? Or population variance, right? If we know, oops, right here, right? If we know the population standard deviation, we also know the population variance, right? Because it's just square the standard deviation to get the variance. We could do a 90% confidence interval, right? There's not much kind of here other than like identifying the correct formula. So in that formula sheet, it's nice that we have all the confidence intervals right here, right? CI. We don't have a proportion, so right away we can rule out this one. And from there, it's just which one of these confidence intervals do we use? Well, we use the one where we have a known population variance because we don't have a sample variance. We have the actual population standard deviation or the population variance. We should be using that standard normal Z table, so this will be the guy that we're using. Plug in, what was it, 109, I think was our sample mean. We got a variance, or we had a standard deviation of, is it 15? Yeah, 15. So once again, be careful. If you're only given the standard deviation, that's just sigma. So when I plug that 15 in here, I still need to square it, right? If I had been given the variance is sigma squared, and I would just be plugging that value in for the numerator. Then I have my sample size of 30. The only thing left to do is find the Z value. So how do we do that? Well, we want the Z value that gives us alpha over 2 on kind of either side of this confidence interval, right? So what we're thinking about is I found this sample mean of 109. I want to find out lower and upper bound such that alpha over 2 is on either side. So how many standard deviations away from that sample mean that I found of 109 do I need to go? Well, what was it? It was a 90% confidence interval? Okay, so my alpha would be what? 0.1, so 0.05 on each side, right? We divide that by 2. So I want 0.05 in that lower left tail. I can do it 2 ways. One, I can just go ahead, use that standard normal table, right? I can get off here, there we go. So 0.05, say it's in between these two. So negative 1.64 and negative 1.65. So I'll use kind of negative 1.65 there. But remember that positive up here, that positive negative is already built in, right? It's negative 1.65 to find the lower bound, positive 1.65 to find the upper bound. So for that Z value, I'll kind of use that 1.65. From there, it's a matter of going to enter in my calculator, right? We've plugged all the values in. We found that Z value now. That should give us our confidence interval. Now, if we look at the possible answers, right, 109 should be centered in the middle of all these. I don't think there's any we can necessarily rule out here. If I'm looking at these real quick, looks like it does split all these in the middle. So didn't give you any that you could rule out on this one. It was a little bit harder. So I don't know. I mean, at that point, it's just a matter of kind of plugging things into your calculator. So we'll just, I'm not going to kind of write all this out. I think that would be not the greatest use of our time. I think the more important part is identifying the correct formula, being able to find that Z value, and then kind of plug and chug. Right? Now here, notice I have it out to the 3rd decimal. How could I do that? Well, I kind of mentioned this last week. I call it cheating, but it's not really cheating. Remember, if I use that student T table, and I wanted 0.05 in that tail, if I look at this last row, these were the standard normal distribution values. If I had a student T with degrees of freedom of infinity, we said the student T eventually becomes that standard normal. Now, in practice, we can't get a degrees of freedom of infinity. That we need a sample size of infinity. That doesn't make any sense. But it's kind of a nice thing that this table has. So instead of like hunting down, like what am I close to in the standard normal table? Well, I can get exactly 0.05 here. And the value out to the 3rd decimal from a standard normal distribution would be 1.645, right? Before we said it was in between 1.64 and 1.65, we can be a little more specific here. Now, if you were to use 1.65 when you were plugging everything in here, right, and you look at the possible answers, what was it, B? Right? I think it's going to be 105, right? You'll be a little bit off. Like I think you end up getting like 105.48 or 49. Like you'd be a little bit off if you kind of used it only the second decimal, but you're never going to be given answers where like it's very close, right? And depending if you used it out to the second or third decimal, I'm never going to kind of present those answers like that. So it should be pretty clear kind of what the correct answer is, even if you're off to like on the second decimal. Okay. Any questions on that one? No, I kind of didn't go through like writing it exactly all, but hopefully showing you exactly what you need to plug in. Okay, so here we got another one where we have to identify the known alternative hypothesis. So let's say I use this information and I want to test for whether or not the IQ is different than the national average of 105. So I want to test for whether or not it's different than, the true mean is different than 105, which is really saying, is it not equal to 105, right? So my alternative hypothesis is that that mean is not equal to 105, which I'll assume the opposite is true for the null, or that it is equal to 105. So here, what type of tailed test do I have? Two-tailed test, right? Because anytime I see a not equal to sign in that alternative, I know I have a two-tailed test, or think about it this way. If I assume it's 105, if I found a sample mean of 109, that goes against it, but I could have also found a sample mean of 101, and that would have went against my null, right? So both sides of the distribution have evidence that goes against this assumed true value. So if I'm thinking about finding critical values here, right, how would I do that? Well, we have a known population standard deviation, so we already said use that standard normal distribution. So I'll use that standard normal distribution and find the z-values that would give me, let's say for the first one, alpha is 0.1. For a two-tailed test, alpha is the total kind of area in the tails because it represents the probability I saw something as far away from the assumed true mean that I did, or something even further that goes against that null hypothesis. Well, now I have two sides, so I've got kind of half of alpha in each side of the distribution, right? So this is where last class I said kind of a nice little thing maybe to jot down, have it next to you before you take the exam, would be, I'll do two-tailed test first. So for a two-tailed test, you want the critical value, but you have a pair of critical values that are the same, but one's positive, one's negative. And you want it such that you have alpha over 2 in each tail, right? Alpha total in the tail, but alpha over 2 in each tail. For a right tail test, we kind of already said our critical value gives us alpha, but it would be positive values. And for a left tail test, it gives you alpha in the left tail, which means that you would have these kind of negative critical values. Right? So here we've got a pair of critical values. Maybe we can look up the first one, though, and we can actually identify what the correct answer is if it's a multiple choice one. So alpha of 0.1, that's what? 0.05 in each tail. We're using a standard normal distribution, so we don't need degrees of freedom here. In fact, a two-tailed test, right, is very similar to a confidence interval. If I wanted the z-value that gives me alpha over 2 on each tail, that's what I'm doing here, right? These critical values are just coming from a standard normal distribution or a z-table, so these are really z-values. So if I want the z-value that gives me 0.05 in the lower left tail, what did I find that it was in the problem before? Negative 1.645, and then positive 1.645 would be the other one. Now, if I didn't have the previous confidence interval problem, I would look up 0.05, in the z-table, go over, find the z-value that gives me that, or I could use that last row of the student t-table. But it'd be the exact same process, right? Because we're still dealing with the same distribution. Confidence interval was using a z distribution or standard normal. So was our hypothesis test. So once I have these critical, this first critical value, and I go to my answers, right? So positive and negative 1.645, that's going to be the answer. I can look the other two up and convince myself of this. Look up what? 0.025 and 0.005. In fact, if I go ahead and do that, I'm going to use this t-table and use the last row. Huh?
I was confused why you used 0.05.
So remember, yeah, I did kind of skip that. So remember here, when alpha was 0.1, For a two-tailed test, we had to divide it by 2. So for an alpha of 0.05 and 0.01, those get divided by 2. So 0.025 and 0.005. So I go here, 0.025, 0.005. Use that last row of the student t-table because that essentially is the standard normal distribution. 1.96, 2.576, which is the other two values, if we wanted to have looked them up. Once we looked at the first one, we can identify the correct answer, though. Okay, so we've got those 3 critical values dealing with this two-tailed test. What if I wanted to find a test statistic? Well, once again, the test statistic problems actually should be fairly easy in the sense that once I identify the correct formula, it's just a matter of plugging values in, right? So I go here to my formula sheet. Here's my test statistic formulas, right? So I have a sample mean, and I know the population variance, or I know the population standard deviation, so I'm going to be dealing with this guy right here. I plug in, what was it, 109. Assume true value from our null alternative was that 105. 15, I think, was the standard deviation. We then square that and then divide by that sample size of 30. Was it 40? Sorry, I mixed it up with the other problem. Not 30. This was 49, right? Our sample size was different on this one. Sorry about that. Our sample size, if we go back, was what? Here, 49, right? So it's really just a matter of plugging things. Now, one thing we could do at this test statistic problem is if we draw this out, and I think this is always a good thing to do. I mean, first of all, like if you draw it out, it reminds you that you're using a two-tailed test. But also, we think about the distribution of my sample means here. But we're assuming the true value is 105. So our sample mean should be centered around that. We found a sample mean of 109. So when we think about, when we turn these into z-values, or our z-statistic, our test statistic, if I use the assumed true value, that should always have a z-value or z-statistic of 0, right? Because that's where that distribution is centered around. So if I see something above the assumed true mean, my z-statistic has to be what? Positive values. If I saw sample evidence below the assumed true mean, I would have to have a z-statistic that is negative. So I found something that was above the assumed true mean, so I know right away my test statistic has to be positive, so I could actually rule out A and D right away. So now it's just a matter of getting those values plugged in. I think, is it 1.8? If we kind of plug those in, let me see. Look at the answer here. So 1.867, right? So once we plug those things in, it's just a matter of getting entered into our calculator correctly. Sorry, I'll that over here. Okay? So if we, oh, I didn't want to do that. I wanted to go back to here. So now, if I want to make a rejection decision, or even in this case, maybe I would have asked you to find a p-value. It's not a problem here, but I could have done that. If you had the wrong test statistic, you might make the wrong decision, right? So instead of making these cascading errors, I said assume that when you turn that into a test statistic, you found negative 2.3. Well, now, that's why I said don't read into these assumed true values, because the actual test statistic is positive, right? But I gave you kind of this assumed true test statistic because I thought it was kind of interesting for a specific reason that I think hopefully we'll see. So the p-value is the probability that I saw the test statistic that I did or something more extreme that went against that null hypothesis. But remember now, evidence on either side would go against it. So I have kind of half, not alpha, sorry. I have half of the p-value kind of in each one of these tails. So once I find the area of one tail, to get the total p-value, I need to multiply by 2, or kind of add these two together. Well, with a standard normal distribution, I can look up 2.3 in the table and find the area to the left of it, sorry, negative 2.3 in the table, find the area to the left of it pretty easily. So I go to my standard normal table, because that's the distribution we said we're using. Go to negative 2.3, 0 would be the second decimal, so that's that first column, 0.0107. Right, yeah, 0.0107. So 0.0107. To get the total p-value, right, that's just half of it. I need to multiply that by 2. So my total p-value, 0.0214. Right? So I can find the area in this tail, but I have to remember I have two tails, so I need to multiply it by 2. If I do that, then I get my total p-value for a two-tailed test. So at what levels could I reject here? Well, my p-value, I only reject if it's less than alpha. So is it less than 0.01? No. So I fail to reject. Is it less than 0.05? Yes. So I reject. And if it's less than 0.05, it's definitely going to be less than 0.10. So I would reject at the 5 and 10% levels here. Okay? Now, you could think of one way to do this. I mean, let's say instead of starting from kind of the lowest alpha, if I'm making my rejection decision, one thing that can kind of help is, let's say I instead started at 0.1. It can sometimes, it just depends, right? Let's say that instead the p-value we had found was, let's say it was 0.007, right? Well, in that case, if I check against the lowest first, is it less than 0.01? Well, yeah. Well, if it's going to be less than 0.01, I know it's going to be less than 0.05 and 0.1 as well. So if I find that I can reject at that 1% significance level, I know I can reject at all, right? So, you know, in this case, it would be nice because I really don't have to kind of continue checking. Now, if I'd had a p-value, say, of 0.13, well, now I have to check if I go against it. It's not going to be less than 0.1, not less than 0.05, not less than 0.1. So I have to check all three. It's kind of a problem. If my p-value is a little bit bigger, notice if I check to see is it less than 0.1, well, it's not, so I'll fail to reject. Well, if it's not less than 0.1, I know it can't be less than the smaller alphas, right? So kind of this idea that if my p-value is small enough where I can reject at the 1% level, I know I can reject at every level. If it's large enough where I fail to reject at the 10% level, I know I'm going to fail to reject it at all levels. So, you know, possible answers that don't make any sense would be if I said something like, I can only reject at the 1% level. Well, if you can only reject at the what value is going to be less than 0.01, but not less than 0.05? I mean, there's no value that fits that criteria, right? So seeing an answer that would be like the 1% level only, or the 1 and 5%, but not the 10%, those don't make any sense. And one way we can kind of remember why is we can translate these to confidence levels, right? So this was like 99, 95. Right? So if I reject at the 99% level, how the hell can I fail to reject with 95% confidence? It doesn't make any sense, right? So the only examples that make sense when you're seeing like this level only is kind of for these higher alphas. Right? So I might only be able to reject at the 10% level. I might only be able to reject at the 10 and the 5% level. But never would I only reject at the 1 or only reject at the 5. Or, you know, so that's one way we can kind of maybe rule some answers out. I think in this one, there's like one answer we can rule out because of that. Right? The 5 and 1% levels, that doesn't make any sense for us. Now, the other three are all possible answers, right? So we had to work it out to figure out that it was only the 10 and the 5. Right? But these are possible answers. Right? Any questions over anything there? What's another way I could have made that rejection decision? Could have used this test statistic of negative 2.3 and plotted it against my critical values here and seen, is it in the rejection region? Right? So if I wanted to have done it that way instead, does everybody have this? Can I erase this? If I want to do that instead, what I'm thinking about there, using those three critical values, are coming from that standard norm or Z. So what? Negative 1.645, positive 1.645. Next one was negative 1.96 and positive 1.96, 2.58, negative 2.58. Here's my rejection region. This is kind of drawing the arrows on the tail. We had negative 2.3. Where would that have fallen? Somewhere like right here. Nope, that was a Z statistic because we were using the standard normal. So it's in the rejection region for that critical value that was corresponding to the 10% level. In the rejection region for that critical value corresponding to the 5% level. not quite in the rejection region for that 1% level. So we make the same rejection decisions, which were, and I erased it, but it was the 10 and the 5, right, with that p-value of 0.02. Okay. Any questions on that?
Do we do a T table one?
Yeah. Let me see, was there one on here? Yes, I didn't have one here. So, let me see. Actually, let's go back to the week 11 lectures. I had some examples there. I think this was one. Yep, let's do this one. Yep. So question 5, this is at the end of week 11 lectures. So we've got smartphone battery life of 4 hours. The manufacturer claims the new phone has a battery life twice as long. The researcher samples 30 phones, finds a sample battery life of 8.9 hours and a sample standard deviation of 2.1. Right? So we want a 90% confidence level. Right? So if we want to find whether or not these phones have, this one's a little bit, I wouldn't give you one this complicated on the exam. But what we want to see is the manufacturer is claiming that it lasts more than the average of 4 hours, right? Twice as long. So if it was, lasted longer than twice 4 hours, it would be greater than 8 hours of battery life, right? That's really what this manufacturer is claiming. So we're going to say, what we want to find is whether or not that claim is true. In fact, is that true mean greater than 2 times 4, right? Twice the battery life. I wouldn't give you something that complicated on the exam. But once we have that known alternative, right? The alternative was that it was greater than 8 hours. We'll assume the opposite is true, which is that's less than or equal to. So we have what type of tail test here? Greater than sign, so right tail. So let's assume we've got these sample means. We're going to assume that they're distributed around that value of 8. And I think I said that the sample mean we found was 8.9. So we've got this null alternative hypothesis. We next want to find the test statistic, critical value, and p-value. Right? So the test statistic, let's go to that formula sheet. Which of these are we going to use? Well, first of all, I believe in the problem, all we were given was a sample standard deviation. So right away, what distribution should we be using? T, student T. So if I go to that formula sheet and I look at these test statistics, right away, if I can remember I use the student T, I know I'm using this one right here. Now, if I look at it, right, it's got the sample mean and only a sample variance or only a sample standard deviation, so I know that I'm going to be using this one. It can remind me I'm using the student T table, right? If all I have is the sample variance or the sample standard deviation, I'm going to be using that student T distribution. Okay? So I've got my sample mean of what? 8.9, assumed true mean of 8. I forget what the variance was, or the standard deviation was 2.1. So I've shown you a lot of examples today where you have to remember if you're only given the standard deviation, 2.1 squared, right, to get that variance there. And then my sample size was what? 30 phones, okay? So I plug those in, and I can hopefully be able to get that test statistic. So I don't know what that ends up working out to be, but we'll kind of write this out up here, and I'll grab my calculator here in a second. So this is what, 2.1 squared divided by 30, right? So I get what? 0.9. So first of all, what did I do wrong here? I was writing this down too fast. What should be first? Yeah, it should be the mean minus the assumed true mean. I was looking at these and writing too quick. Right, the assumed true mean we had was 8. So right away, my test statistic should be what? If it's something above it, it has to be positive. That's why when I looked at this automatically, I knew I made a mistake. So I said, well, if I look at the drawing, I know this has to be a positive test statistic. When I started entering this in, I saw it was going to be negative. I was like, oh, I made a mistake, right? So this is what, 2.35? second decimal. Okay? So if we wanted our critical values, what we're thinking about there is, if I were to turn, right, this into a test statistic and plot that test statistic against my critical values, what would they be? Well, here I know my critical values have to be positive, right? We're going to do this example where we have one specific alpha we want to test against, I think. So let's do the 90% confidence. So alpha is 0.1. So we know what we're looking for is the critical value that gives me alpha of 0.1 in that upper right tail. What would be my degrees of freedom here? Degrees of freedom is simply n minus 1, so 30 minus 1 or 29. So it happens to be the same as the problem we were working at earlier, but that's okay, right? Our degrees of freedom is what it is, right? So we'll go to that student T table. We have a degrees of freedom of 29, so we're all the way down here, but the area we wanted in our tail was 0.1. So 0.1, go down to degrees of freedom 29, 1.311, right? So that will be our critical value. So here, this critical value would be 1.311. Now, at that point, we found the critical value. That was what the question was asking for. But if I had said, can I reject at that 10% significance level? Well, I plot my test statistic. It would be somewhere over here. This was actually a T statistic here. So clearly, once I have that critical value, my rejection region, anything more extreme or greater in absolute value, or draw the arrow to the tail, my test statistic is pretty clearly in that rejection region. So I could reject at the 10% level. Now, if I was using the student T distribution, and I asked you to find a p-value, right, which on the exam I would give you a test statistic that you wouldn't have to put a bounds on it, right? Or I just won't ask you to do it. But we'll work through it, and if you understand how to put a bounds, you'll understand if you had, your exact test statistic from the table would be even easier. So can I kind of find the p-value here, which would be the probability I saw this test statistic or anything kind of further from that assumed true mean. Or you can think about it here, right? This is my p-value. If I want to find that, I have to turn this into a z-value so I can use those, a t-value so I can use that student T distribution table. So I got degrees of freedom of 29, test statistic of 2.35. So 29, 2.35. Sure enough, not in this table, so all I can do is put a bounds on the p-value. So I know that my test statistic is somewhere in between these two values. So my p-value is somewhere in between 0.01 and 0.025, right? So my p-value is somewhere in between this. So I'll write that out. So I guess here. So what was it? 0.01 and 0.025, right? So what levels can I reject at? Well, here I only have one that I really need to test it against. I was told, check to see if it's at the alpha of 0.1 or the kind of 10% significance level. So is my p-value less than that alpha of 0.1? Well, if it's between 0.01 and 0.025, if I know it's less than 0.025, it's definitely going to be less than 1, or sorry, not less than 1, less than 0.1, so I can reject here. And what could help, like I said, I shouldn't ask you to do any of these bounds ones, but you could almost, maybe a good way to think about it was, if I know the p-value is somewhere in this range, just choose a value that fits that criteria, and then maybe it's not as confusing. So what's a value that would be in between this? So 0.015. Well, now that I have this kind of hypothetical p-value, now I can say, okay, is 0.015, is that less than 0.1? Yeah, so I could reject. I could even check different alphas. Is it less than 0.05? Yes, I can reject. Is it less than 0.01? No, I'll fail to reject. And as long as I choose a value that is in that range, I'll be okay doing it this way. Right? That might make it a little bit easier. Any other questions or questions on that one? Okay on that? Yeah.
How long is the test?
So it'll be 20 multiple choice questions, and then kind of a short answer question at the end. Oh, time limit, hour and 20 minutes, so 80 minutes. I think it should be fine on time. I mean, based off of exams I usually give in class with, maybe more limited materials. Usually the second exam takes people a little bit longer. That short answer is worth 20 points. So, if you're working through and you realize you don't have a ton of time left, I would make sure I kind of devote some time to that short answer question, so you don't kind of forget about it being at the end. Each multiple choice question is worth 4 points, so that kind of gives you a total of like 80 points for multiple choice, and then that last short answer has like 4 parts, each part being worth kind of, there's a couple that are a little bit off, but all approximately 4 to 6 points, kind of be all adding up to 20 points there. Yep, upload, you could use, upload a Word file, Excel if you do some of the work in there, a picture of your work that you did by hand, but make sure you show as much of your work as possible, right? Because if you give me just an answer and it's wrong, I can't give you any partial credit for that. If you give me a wrong answer and I can see you did every step right, but maybe I already erased it, but maybe when you plugged it in, you forgot to square the standard deviation, you're going to get hardly any points taken away if that's the only mistake you made in calculating the test statistic, right? So make sure you show me as much work as possible in that short answer portion, to ensure that I can kind of give you as much partial credit if you do make a small mistake. Okay? Yeah. Oh, sorry.
Do we have to use like the lockdown browser?
No. So it'll be like last time. There won't be a lockdown browser. I'm kind of, hoping you guys kind of hold to that kind of academic integrity. Don't talk with other people as you're working on these. I mean, not going to see exactly the same thing anyways, so maybe if you do that, I've had in the past where I gave 2 different forms of the exams and students didn't realize, and some kid, they're clearly cheating and one person got like everything wrong because they had a completely different form and the answers were, so I even if you want to cheat, I would highly recommend, it's not going to help you out because of some of the things I did if you don't realize it. So, but yeah, no lockdown browser. You can use Excel. If you're comfortable with those functions in Excel, you can use that. Obviously I didn't put the answers on the exam like that because you'd be able to get way more specific in terms of the decimal. So all the answers, I did the calculations by hand, assuming that you would have to round kind of that third or second decimal. So that's how you would. So if you did it in Excel, you'll be off a little bit, right? Because you'd have to round it, or just round your answer in Excel to the second or third decimal, and that should be what you see as the answers displayed. Any other questions? Okay. All right. If you have any last minute questions as you're studying, I'll be I have some other classes I teach today, but after that, I'll be pretty available via email. If you want to schedule time to kind of drop in, meet up with me either later this afternoon or even tomorrow before you start the exam, if you want to take the exam tomorrow, email me, set up a Zoom meeting, or you can kind of schedule time to meet me in person. Other than that, good luck, and I will see you guys on Wednesday.